Hi everyone, my name is Zhong Zheng. I'm an undergraduate student at Peking University. In the next 20 minutes, I'm going to introduce a new data structure which can find burst items in high-speed data streams in real time. And we call the data structure BurstSketch. Part 1 is about the background. The data stream model is that items will appear in a time sequence one by one. One distinct items can appear multiple times. For example, E1 appears 3 times in this sequence. Therefore, one challenge about the high-speed data streams process is that we must process it very fast. Otherwise, we may lose items. Our target, burst, is a common pattern in data streams, which is characterized by a certain increase in terms of arrival rate followed by a certain decrease of a distinct item. Let's see an example. These two patterns are bursts. We can see the number of these items first increase sharply and then decrease sharply. Let's say another example. This is a timeline. At first, we divide the timeline into many time windows. In the first window, the item appears several times. In the second window, the item appears much more times than the first window. Specifically, when the number of appearances in the current window is k times larger than the previous window, we regard that a certain increase occurs. In this case, the second window is the second increase window. The third window's frequency seems similar to the second window, and also the fourth and the fifth windows. In the sixth window, the item appears much less than the fifth window. Specifically, when the number of appearances in the current window is 1 over k times smaller than the previous window, we regard that a certain decrease occurs. In this case, the sixth window is the second decrease window. And we regard the number of windows the burst lasts as burst width, which is 4 in this case. We also define that the burst frequency of the windows between the second increase window and the second decrease window must be higher than a burst threshold. Because first, we usually do not care about infrequent items burst in practice. Second, if an item's frequency in the recent-free window is 0, 1, 0, it also has certain increase and certain decrease. But regard this kind of pattern as a burst is obviously unreasonable. Burst is important in abnormal detection. It has a lot of applications in multiple areas. In financial area, if a burst of a user's transaction occurs, it may mean a financial fraud or market manipulation happens. In the network area, bandwidth is a variable resource. You can see this line is the bandwidth level, which normally can cover the traffic volume. However, when a burst occurs, the traffic volume will higher than the bandwidth limit, and some network packets will be discarded, which will cause severe problems. Burst in a network usually means a network attack or error happens. So, we should find which items burst in time and handle the attack or fix the error. In the data mining area, when the searching times of a word burst, it may mean some noticeable event occur. We can see that the searching times of Biden burst in November 1st to November 7th. And we all know that these days, people were holding the American election. So, our task is real-time burst detection in high-speed data streams. The design goal of the data structure is fast, accurate, and compact. Because the data structure has to handle high-speed data streams, the insertion speed must be very high. The data structure should be compact so that the cache can hold the entire data structure to raise its speed, or the data structure can be held by network switches to detect network burst. To find burst accurately, its precision rate and recall rate must be high. These two metrics I will elaborate on in the experiment part. To satisfy these design goals, we believe a kind of probabilistic algorithm, sketch, is the best solution. Sketch's insertion speed and query speed are very fast. The time complexity is O1. Sketches are extreme compact, and its accuracy is controllable. It means that when we think the sketch's accuracy is not high enough, we can give it more memory to raise its accuracy. The second part is the algorithm. First, we introduce the most classic sketch algorithm, count-min sketch, aka CM sketch. We use O1 time to insert every item in the data stream. When we query it, the count-min sketch can report an arbitrary item's frequency. The strawman solution of burst detection uses count-min sketch. We use m count-min sketches to record the latest m time window's frequency. The first count-min sketch records the first time window, and the second count-min sketch records the second time window, and so on. Now we know the latest m time window's frequency. So we just check each item if they burst in the latest m time windows. If we find a pattern like this, we report a burst occurring. This approach can detect bursts smaller than m-2 windows. However, in this way, the time complexity and space complexity of each item are both OM. And in contrast, these two complexity of BurstSketch are O1. BurstSketch has two stages, Stage 1 and Stage 2. Stage 1 is like a filter. It selects potential bursts and inserts them into Stage 2. Stage 2 storage potential bursts and double-check if there is really a burst occurring. Each item inserted to BurstSketch will first be inserted to Stage 1, then be inserted to Stage 2. Stage 1 uses the technique of running check to select potential burst items and send them to Stage 2. The technique of running check means that we randomly send items to different running check and let the items in the same check compete. The fastest item, that is, the champion of each check, has a chance to be regarded as potential burst. We can see that lots of items are inserted into the Stage 1, and just a few items will be regarded as potential items. And the non-potential items, that is, items with a small arrival rate, will be filtered out in Stage 1. Our experimental results show that, in our dataset, 87% of items are filtered out, while almost no burst item is filtered out wrongly by Stage 1. Stage 1 is a hash bucket array. Each bucket records an item's ID and frequency. For an incoming item, we hash it into D hash buckets. In this example, D equals 1. If the hash bucket is empty, we insert the item in it and set the frequency as 1. If the incoming item's ID and the bucket's ID are the same, we increase the frequency by 1. If the item's ID is different from the bucket's ID, the incoming ID will try to evade the bucket's ID, so the bucket's frequency will be decreased by 1. And when our bucket's frequency is decreased to 0, like E7, the ID will be evaded, and the bucket will be cleaned to empty. The idea of this strategy is that high-speed items can increase their frequency very fast. Therefore, although other items occasionally decay the frequency will not become 0, and the high-speed item would not be evaded. In contrast, if a slow item, which is not likely to become a burst item, occupies a hash bucket, the slow item's frequency will be decreased to 0 rapidly and be evaded. However, if two high-speed items are hashed into the same bucket, the hash collision will occur, and one of them will be discarded. Therefore, normally we set d larger than 1. In this way, each item will be hashed into more than one bucket, just like I mentioned before. Each item will be sent to more than one running check. As long as the item speed is fastest in at least one bucket, the item can win the race and can be regarded as potential burst. So, when the item's frequency reaches a threshold, which is 50 in the example, the item will be regarded as a potential burst, and it will be sent to stage 2. After that, the bucket in stage 1 will be cleaned to be empty. At the end of each window, we will clean the whole stage 1. In this way, slow items will be filtered out, and fast items will be inserted into stage 2. All potential burst items in stage 1 will be inserted to stage 2. Stage 2 uses snapshotting to monitor if there is a burst occurring. The snapshotting means that we would not record the in-time pattern of a burst. Instead, we just take a snapshot when the burst speed suddenly increase or suddenly decrease. Because the sudden increase and the sudden decrease can directly characterize the burst. Therefore, the complexity of the insertion speed and space is O1. Stage 2 is also a bucket array. Differently, each bucket in stage 2 can storage more than one item. In this example, can storage 4 items. To accurately detect burst, for each potential burst item, we record 4 of its information. They are the item's ID, its frequency in the previous window, its frequency in the current window, and the newest second increase window's number. Similarly, for each item inserted into stage 2, we will hash it into a hash bucket. If a bucket is not full, we insert the item into the bucket. Notice that 50 E4 items were inserted into stage 2. So we insert E4 into the bucket and initialize its frequency in the current window to 50. If an incoming item's ID has already been in stage 2, we will directly insert it into stage 2 because it has already been a potential burst. The result is that its frequency in the current window increased by 1. At the end of each time window, we will scan the whole stage 2 to check if bursts occur. Suppose the burst threshold is 100, which means the frequency of the windows between the burst sudden increase and sudden decrease window must higher than 100. The frequency of E9 in the recent 2 time windows is both lower than the burst threshold. Therefore, we think E9 is no more a potential burst and evade it from the stage 2. For E10, its frequency in the current window is lower than the burst threshold. So we clean its newest sudden increase window's number to 0 to make sure this illegal burst will not be reported. Suppose the parameter k is 2, where k is related to the definition of sudden increase and sudden decrease. For E11, we find that its frequency in the current window is 2 times larger than the previous window, so we know a sudden increase happened. To record the sudden increase, we recall the current window's number to its newest sudden increase window's number. In this example, the number is 8. Similarly, for E12, we find that its frequency in the current window is 1 over 2 times smaller than the previous window. So we know a sudden decrease happened. And the bucket records that E12 newest sudden increase is in the third time window, so we report a 5-time Windows burst of E12 occurs and clean the newest sudden increase Windows number to 0. We also have an optimization version to reduce deprecation. It can raise the accuracy of BurstSketch. The specific approach is in the paper. The final part is about the experimental result. We use anonymized IP trace streams from SIDA as our dataset. The number of total items is 20 million, and we set each window to include 40,000 items. Our metric is recall rate, precision rate, and throughput. Recall rate is the ratio of the number of correctly reported to the number of true instances. Precision rate is the ratio of number of correctly reported to the number of reported instances. Throughput is million insertion per second. We can see that our recall rate and precision rate are much better than the strawman solution. When the memory usage is 100 KB, the recall rate of our basic version is over 97%, and the optimization version is over 98%. The precision rate of BurstSketch is over 98% in all memory usage. The conclusion is, using a small amount of memory, BurstSketch's accuracy is very high. Let's see the throughput result. BurstSketch's throughput outperforms the strawman solution. We find that the parameter D in the optimization version is a trade-off between accuracy and throughput. The throughput drops with the increasing D, when the accuracy grows with the increasing D. The throughput of BurstSketch with D equals 1 can achieve 1.6 million insertions per second. We also have an extended version to detect bursts inside burst. In our basic version, only the middle burst with the largest peak value will be regarded as a burst. It can make sure there is just up to one burst in the very moment. In the extended version, we also regard the bottom one as burst since it also has a certain increase and a certain decrease. So there are two bursts. We call the middle one burst inside burst. The specific algorithm of the extended version is in the paper, and the experimental result is its recall rate and precision rate just drop a little compared to the basic version. Now introduce two main relative work, which is Topic Sketch and CMPBE. In fact, the differences between our algorithm and these two algorithms is very large. First, the definition of burst is different. These two works regard large acceleration as burst, while we regard a pulse-like pattern as burst. The result is, we cannot detect the burst they defined, and they cannot detect the burst we defined. Second, the focus of three algorithms is different. Topic Sketch can only detect burst events on Twitter, while our detection is general. CMPBE focuses on burst detection in history, while we focus on real-time burst detection. Third, these two algorithms just use the most classic sketch, count-min sketch, to detect burst, while we used more advanced sketches algorithm to raise our accuracy. The last page is about the conclusion. Burst is a common pattern in data streams and is useful in abnormal detection. BurstSketch can detect bursts accurately with small memory usage in high-speed data streams. For example, when the memory usage is 100 KB, the recall rate and precision rate is over 98% in our dataset. And our code is open sourced in GitHub. That's my talk. Thank you.